Now we welcome Muhammad Yaseen Ayub, who will be speaking on computer vision and machine learning for sheep activity detection. I request Muhammad Yaseen Ayub to share the screen and start the presentation.
Okay, let me know when my screen is visible. First of all, thanks a lot to all of the organizers for giving me this opportunity. And is my screen visible now?
Yes, it is visible. You can proceed.
Okay, so the topic of my presentation, the thing I'm going to present is exploiting computer vision and machine learning for sheep activity detection. So let's first have a look at why do we even need to detect their activity. So there could be various reasons and benefits of detecting sheep activity, such as improved animal health, improved efficiency of management, virtual fencing, or automated detection of irregularities in the farm, improved breeding, or improved in general improved tracking. So this project aligns perfectly with HEC's research priority areas. The section D perfectly aligns with this. And not only the HEC, this project also aligns with some other international organizations and their research priority and development areas, such as Food and Agriculture Organization of the United Nations, World Health Organization, and World Organization for Animal Health. Similarly, this also comes under the umbrella of United Nations Sustainable Development Goals. Moving along from that, as from the previous slides, we can see that animal activity detection is one of the hot research topics, which also comes under the umbrella of United Nations Sustainable Development Goals, as we saw in previous slide. So, what can be some uses of the application of monitoring sheep activity? Let's have a look at that. Primarily, there are some application which could be of our use, such as monitoring sheep activity or monitoring other animals' activities as well in a zoo. A model can be trained which can monitor the activity of other animals in a zoo, and there would be less need of specialized persons who keep a check on all the animals. You could train a model which can detect your pet's activity at home while you are away, or most importantly, it can be used for virtual fencing. But before jumping to virtual fencing, let's have a look at how people have fenced their livestock farm in past. Livestock farming started around 11,000 years ago from now, and history tells us that till the 17th century there was little to no change in farming methods, and people used to herd their animal themselves or hire a group of people to herd them. They also used sheepdogs and trained them to control the flock movement. But these all the old methods. Here are some pictorial representations of how people used to herd their livestock farm. Okay, these methods are human resource intensive. Also, they are not suitable for a large number of animals. For example, a farm could easily have 50,000 plus sheep, which is very common in countries like United Kingdom and Australia. So it is not physically possible for humans to herd a flock of like 50,000 sheep. And human cannot also monitor and maintain very large number of animals. If a sheep is like ill or it's sick, it's showing some lameness, a human cannot detect that in a large flock. And after physically maintaining the livestock farms, humans started to fence their farms using brick walls, but that turned out to be way too expensive. Then humans started fencing farm with a wooden fence, and it was a bit less costly compared to the brick wall, but still not affordable if you have to fence a very large area. Here's some pictures depicting how wooden fence would be used, and if the fence is not high enough, the sheep can just like jump over the fence. Now imagine you have to fence a 5,000-acre land. How much will it cost? For example, 10-meter fencing cost 100 pounds, then fencing 5,000-acre will cost approximately 6.38 million pounds. So, do you see the problem with the growth in the size of farm? Cost is directly proportional to it, and it quickly becomes unaffordable. Also, sheep and other animals can break the wooden or metallic wires over time by simply hitting them. So, to solve this problem, humans started to install electric wire fence, but quickly it caught the attention of animal rights activists and was declared illegal in many countries as several animals died due to electrocution. Recently, researchers started using sensors to monitor sheep activity. Sensors are placed on their collar belt or on various other locations, sometimes on their leg. And if the animal is going out of range of the fence stone or out of the range of the farm, they give a mild shock to the animal. No physical fence existed, so this solution was a bit cost effective, but still animal rights activists got it banned in several countries due to electric shock being involved. Researchers came up with annoying sound frequencies as a deterrent instead of electric shock. So, if the animal is going out of range, instead of giving them a electric shock, they will turn on an annoying sound frequencies. It has been proven by research that from 144 hertz to 450 hertz of white noise is very annoying for most of the livestock animals, and they try to avoid that. They try to go in the opposite direction from the source of that frequency. This was somewhat acceptable to the animal rights activists as there was no electrocution involved, but still it is very costly if done at a larger scale. As the population is growing, so we need more and more larger farms. Let's suppose we have a farm of 50,000 sheep, which is very common in countries like United Kingdom and Australia. Let's suppose one collar belt with multiple sensors cost up to 25 pound. On average, its cost is from around 20 to 35 pounds. So let's take 25 pound for our example. Now, if we have 50,000 sheep in a farm, it will still cost us 1.2 million pounds to have a collar belt for each sheep in the farm. So it's still very expensive. From previous slides, we can learn that traditional methods are ineffective at a larger scales. They are too costly, and the more recent sensor-based approach, even the one with the annoying sound frequencies, they tend to be somewhat effective, but its cost is directly proportional to the number of animals in a farm. And physical fencing and virtual fencing using sensor belt can cost up to millions of pounds. Now, what our project does, we explored computer vision based deep learning models for sheep activity detection. We took as a sheep as an example. It could be done for various other type of livestock animals as well. It can work for goats and other animals as well. But in our case, for this proof of concept, we took sheep as the example. So we used YOLO V5 small models with 7.2 million parameters. We fine-tuned that model, and we used deep transfer learning methodologies on YOLO V5 model, which is basically the process of fine-tuning them. There were some challenges faced in this project. First and the biggest challenge faced was unavailability of the data set for sheep activity detection. There are some sheep related data sets available, but they were primarily big for sheep detection, not for the sheep activity detection. Since for sheep activity detection, we will need a labeled data set with the ID or with their activities labeled. So there was no such data set available. And the other big challenge for us was deep learning and computer based models require high performance CPUs or preferably GPUs for training. And let's have a look how these challenges were handled. We recorded our own sheep activity data sets after ethics approval from FIP committee of my university. And after collecting the data set, we annotated it in the required format. And for the GPU, we were provided virtual access of four NVIDIA GeForce 2080 Ti GPUs of Applied Computing Research Group of Liverpool John Moss University, United Kingdom. Basically, this project is part of my final year project of my bachelor's degree, and I did that final year project in collaboration with Applied Computing Research Group of Liverpool John Moss University. So the GPU, for the GPU, they provided virtual access of their GPU. So recording data sets. Each sheep activity is recorded from two different angles, a side pose and a front pose. This is a sample image from the dataset, and sheeps of various age and size are recorded. The structure of dataset folder. A folder of annotated dataset contains five different activities, and in each activity then there are subfolder of front or side pose, and then in each pose there are up to 50 individual folders for individual sheets, and each folder contains then picture data, video data, and the labeled XML files. The architecture of YOLO 5 model and the system used for training. Basically, the virtual access was provided by the said group, and this was the system used for training. So after more than 9 hours of training on collective 44 GB GPUs, here are some results we obtained. And as you can see, there are some very nice box and class loss curves. The confusion matrix, which we will see the actual results later on, the picture results where the model displayed the output, the F1 curve, because only just accuracy is not a good matrix of telling that if the model is performing well or not. We need to look for some other parameters like F1 cores, CNN recall, etc. So these things exist in this presentation because this was my final year project, so I had to go in very much detail, but here the time is restricted to 15 minutes, so I will quickly pass through these slides and show you the results. So this is a picture of validation batch 0, validation batch 1. You can see we received quite good accuracy at detecting the sheep activity. Let's have a look at output on unseen data. So we recorded some additional images of sheep and then fed that to our model. You can see the model is 98% confident that the sheep is grazing. And also, if you look towards the right side of the screen, you can see just a little portion of a head is visible, and the model was able to confidently label it as the sheep that is grazing there. This is an instant where model is 94% confident that sheep is running. And here for walking, for sitting. So we detected various activities in our proof of concept. Now we give video as input to the model and get a video labeled by the model. You can see the sheep is running and there are some donkeys in the background, but the model has totally ignored them because our object of focus was sheep. We needed to detect sheep activity. Here is another video where sheep is sitting, and another one sitting, grazing. And here you can see the transition of activity. It is grazing. Now the moment it bends its legs, you can see the label change to sit. So the model was performing very good and it was fit for real time sheep activity detection. So how our system can be used for virtual fencing? We have trained the model after creating the data set, but how it's gonna be used in virtual fencing? Let's have a look at that. So for example, consider this as a form rectangular form, and these small things you can see in between are shapes. It's not up to the scale, but just for a representation. And you can see these brown round dots are the nodes. Small ball with a camera and a speaker on it, and in between the form there would be lots of sheep. And now, for example, if from any point sheep tries to escape the form, the fenced region, each of the pole will be around at 200 to 300-meter distance. And the moment any sheep tries to go out of the form, a 400 hertz white noise will be generated as sheep approaches near the edge of the form, and that will quickly them off. The sheep will turn back away from the source of the noise. That's how you can restrict them inside the form without being needed to purchase a set of sensor for each sheep, or without the need of like physically fencing the complete form. This virtual fencing approach has like greatly reduced the cost, and more cost can be reduced by introducing few drones instead of fixed nodes. So let me move back to previous slide. You can see here that for a large form, a lot of nodes will be required. It will still be way more cost effective compared to purchasing individual sensor for each sheep or fencing the complete farm, but it is still bit costly. What you can do is reduce more cost by installing just four poles with a camera and speaker on each of the corner of the form. And what it does is the field of view of those four cameras capture the entire form. So as soon as sheep tries to go away from the farm or tries to escape the fenced region, a drone, as the four cameras are having the field of view of the whole farm, and they can detect the activity of the sheep, and they can tell you if the sheep is running away. There will be a drone with a speaker on it, landed on its wireless charging pad, so its battery is all full at all times. And the moment model tells the drone which part of the farm the sheep is escaping out of range, the drone can fly in that direction, come around in front of sheep, and generate that 400 hertz white noise, and wear the sheep off, and the sheep can like be herded. What we plan to do in future, we plan on expanding our dataset by recording more activities. The primary activity we are looking for is lameness, so we can detect if there is a sheep which has fallen sick inside a farm. We are looking to explore more advanced deep learning models such as mean shift, deep sort, and some other models. We want to explore deep sort, so we can track each sheep individually. We are planning on working on profiling, so inside a farm the owner can get all the data on his mobile screen, that how much percentage of sheep are grazing, how much are resting, if a particular sheep is displaying sub abnormalities such as it didn't eat in the morning and is continuously sitting, and we can report that the sheep is uh, sick, so they can have a look at that. So thank you. That's all from my side. You can scan it to get presentation slides if you want. And are there any questions?
Thank you, Muhammad Yaseen Ayub, for your enlightening presentation. Does anyone have any questions or comments for Yaseen Ayub before we move forward?
I guess there are no questions. Thanks a lot.
Thank you so much for your kind words and participation.